All right, on to section 1.3, where we're looking at rates of change and behaviors of graph. So rates of change come up in all different places in math, and so we're just going to kind of touch on that in relation to the inputs and outputs, and then we're going to talk about how that we can identify some increasing and decreasing as well as max and mins of graphs. So since functions represent how an output quantity varies with an input quantity, it is natural to ask about the rate at which values of a function are changing. This is referred to as the rate of change. Rate of change. And so the rate of change is how the output quantity changes in relation to the input quantity. And so the units that we look at with rates of change are basically your output units per your input units. Okay, so lots of things that you might be familiar with. For instance, wages. So I make $9 per hour, or whatever the case may be. That is a rate for wages, okay? If I have a car that has 27 miles to the gallon, miles per gallon, for our gas mileage of our car, that would be considered as a rate as well. If I end up planting 60,000 onions per acre, that is also another example of a rate of change. They're all over the place. When we get into mathematical terms and lines and such, then we are going to be talking about the rate at which a line is increasing or decreasing. And it also kind of evolves further into calculus as well with rates of change. Okay? Now, if we go buy a car on a lot, it'll have a sticker on it that says you get 27 miles to the gallon on the highway and only 24 miles to the gallon in the city. So those rates of change aren't always the same. So we sometimes look at an average rate of change there in which we are calculating things. So the average rate of change between two input values is the total change of the function. Now remember, the function value are the output values, or the y values, divided by the change in the input values. So mathematically speaking, a lot of times we will do like change in y over change in x. That little triangle symbol means delta as a Greek letter. And in math it means change in. So the change in y over the change in x, which we could also equate that to subtracting two y values or two output values while subtracting two x values on the denominator. And you want to go from right to left, larger to smaller. And in a function notation, we can also look at it as like f of b minus f of a all over b minus a, where f is on the interval AB. Okay? Sorry. A comma B. All right. So, multiple ways to look at it. Basically, we're taking a y minus a y over an x minus an x. So, for instance, we have an average cost here in dollars of the gallon of gas t years after 2000. Find the average rate of change between 2000 and 2009. Well, notice the t is in years after 2000. So, 2007 is 7 years after 2000, and 2009 is 9 years after 2000. So, those are our two x values that we're looking at. With the corresponding y values is 2.64 and 2.14. So, if I'm asking for the average rate of change, okay, we need to take a y minus a y over an x minus an x. So we need to take this minus this, so take the b first, the bigger number first, and then take x minus x. So it is just a difference. 2.14 minus 2.64 all over 9 minus 7. Y minus y over x minus x. Now, 2.14 minus 2.64 is negative 50 cents out of 2. And when we divide that by 2, we get negative 25 cents per gallon are the units, because the output value has a money unit and the input value is gallons. So you're decreasing, the average rate of change is that you're decreasing 25 cents per gallon from 2007 to 2009. That is the meaning. Now, what if we look at a graph and try to find the average rate of change on a graph with the values from x equaling 0 to x equaling 3? So if this is given to me, I'm probably going to locate when x equals 0, what is that point? It is the point 0, 1. And when x equals 3, over here I have the point on my graph of 3, 4. Those are very important because those are the x's and the y's. So in order to find the average rate of change, I want to take the y value minus the y value. So our average rate of change is equal to taking a y minus a y, so a 4 minus a 1, all over the corresponding x value, which is this 3 minus that 0. And so we do the computation on the top, which is 3, computation on the bottom, which is also 3, and divide those together to give us a 1. So for every change in 1y, if I were to do it as a fraction, change in 1 unit in the y direction, I have a 1 unit change in the x direction. If I were to write it as like a 1 over 1, we can do meaning there. Okay. Now, what if given a function, can you find the average rate of change? Again, I have an x value here and an x value there from the interval 2 to 4. So I need to find the matching y value. So if I plug in 2 and 4 into my function, I can find the matching y values that I have, okay? So f of 4, now our rule is to square our number, then subtract 3. So I have to do 4 squared and subtract 3. Down here I have to do 2 squared and subtract 3. That rule stays the same, the number changes. So square first, then subtract. 4 squared is 16, minus 3 is 13. 2 squared is 4 minus 3, which is 1. And so here comes my average rate of change. Then, I have to take a y minus a y. Now remember, here's my bigger x value, so we have to take the 13 minus the 1 all over the 4 minus the 2. So y minus y over x minus x, 13 minus 1 is 12. 4 minus 2 is 2, and 12 divided by 2 is 6. Therefore, the average rate of change for that function is 6. Okay. Sorry about all those pop-ups. All right, so that's the first piece of section 1.3. The last piece is talking about the behavior of increasing, decreasing, and constant. So what happens on a function when we're going kind of left to right. And we're exploring how functions change. It's interesting to explore the graphical behaviors of functions. We are going to, at this point, or this time, go over two main ones, increasing, decreasing, and max and min. So increasing means you go up, right? Decreasing means you go down. So that's the same for any functions. Mathematically, in order for something to be increasing, on an open interval I, if f of b is greater than f of a whenever b is greater than a. So the y value is bigger than the previous y value as long as b is bigger than a. Okay? A function is decreasing on an open interval I if f of b is less than f of a when b is greater than a. And finally, We're not going up and we're not going down. We are staying the same, which is constant. So we have a constant function on an open interval if not greater than or less than, but if f of a, or excuse me, f of b is equal to f of a. So greater than, you are increasing, less than, you are decreasing, equal to, we are constant. So on the next page, you can kind of see what that looks like. Here is a function that is increasing, going left to right, and read it like a book. Going left to right here, we're going down on our function, and here we are staying the same. That is our constant function. So here, instead of a's and b's, they use x1, x2, but this is like the a and that's like the b. Okay? All right, so now we're going to determine the intervals at which we are increasing, decreasing, and constant on each one of these graphs. So start from left to right, and we're doing this in relation to our x values. So notice, I see my arrow, which means I'm coming from negative infinity, and I keep going up and up and up and up and up until I get to this point right here, okay? So I'm going up, 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 up. Now, we don't look at the y values here, we're looking at the x values. And what's happening from here along this way, our function is going up until I get to that point, which is at negative 1. So from negative infinity, I'm constantly increasing until I get to negative 1. So from negative infinity to negative 1. Now, there will be no brackets here. This is a parenthesis. Oops, negative 1. So at the point of intersection where it changes, it is neither increasing nor decreasing. So we do not want a bracket. We want a parenthesis. Okay? Now, what happens at negative 1? I go down, down, down until I get to this point, which is at x equaling 1. Now, remember, you're just looking at the x values to put in your intervals for increasing, decreasing. So from negative 1 to 1, I'm going down. That is decreasing. Negative 1 to 1. Again, we're not doing any brackets, just parentheses. Then what happens at x equaling 1? Well, for my function, that means I keep going up and up and up. That means we're increasing from 1 to infinity. So increasing from 1 to infinity. That's the only situation that happens. Therefore, there is no constant interval in this function. Okay? Next one, I'm starting here at negative 1. Nothing from negative infinity. I'm starting at negative 1. And what's happening each time? There is no change. There is no turnaround or anything like that. We are consistently increasing from negative 1 to infinity. And therefore, there is no decreasing section nor constant section. Now, this next graph, notice that it's a flat line here. We are constant. It is the same there. It is the same there, okay? So where are we coming from? And the x values were coming from negative infinity, and I stop right here at negative 4. Negative infinity to negative 4 is constant. Then, from negative 4, I go down to this point. So from negative 4 to positive 2. Everything in between here, my function is going down. So from negative 4 to negative 2, that is the decreasing interval. And then at x equaling 2 to infinity, I am also constant again. So we're going to do our little union and do 2 to infinity, and that gives me my constant solution there. No increasing piece here at all. Okay? All right, now, when we are increasing and we get to this point, I kind of max out at a certain point and I come back down, I bottom out at this point, and then I go back up. And that's what we refer to down here as our last little topic of section 1.3 as local maximum and local minimums, or else referred to as local extremum. So if I change from increasing on my function to decreasing on my function. So I go up and I go down. What happens? It's like I'm climbing a mountain. I go up and I come down. I have a maximum point. We call that a local maximum. Okay? if I end up changing from decreasing to increasing on my function, oops. So that means that I'm decreasing and I'm increasing. What happens? I have a bottom out point. I have a minimum there, and we refer to that as a local minimum. And together, as prefaced in the box above, or in that same box, they are referred to at local extrema. That's what we refer to as that. Okay, not all the time will you have a max, not all the time will you have a min. And you may not have either in situations like that. So here's kind of a picture. Again, decreasing, bottom out, increasing, then I top out as a max and come back down. So that's another visual for you. So how do we refer to local max and mins on our graph? It is very important that you know kind of the ordered pair of each one of those pieces. So I'm decreasing here until I get to this part right here, okay? Then I'm going back up. So if you just kind of look at this piece here, I have a minimum value. Who cares about the rest, but I have a minimum value. That is at the point, say, -2, and I'm going to guesstimate, let's say, 1.8, okay? So I refer to that, and that is a minimum, decreasing then increasing. So I have a local minimum at 1.8 when x equals -2. The max of the min is actually a y value, but we identify it where it's located when x equals whatever number, okay? So now I am increasing from my minimum, but then I end up decreasing back down. Here I have an ordered pair, and that one's a little bit nicer. I'm going to call that 0, 3. And what happens here, if I am increasing then decreasing, then I end up having a max. So I maxed out there, and it will be at the y value, so at 3, when x equals 0. So you want to use both values there. You want to use the x and you want to use the y. Okay? And then finally, to finish out our graph, we want to get all the way through. So I'm maxed out here. I'm decreasing till I get down to this piece. There's a delay. And then I'm going to increase back again, creating one of those bottom out points or a minimum. And so then, what value is that point? Well, let's see. We're going to guesstimate here. I'm going to say 3.5 is the x value, and let's go -3 point something. What did I write? -3.25, let's say. So our minimum this time, we have another minimum at -3.25 when x equals 3.5. And that will give us a description of where our local minimum is on this function, and it's actually a quartic function, or excuse me, not a quartic function, it's a power of 4 function, which we will learn later. Okay? All right, very good. So that gives us some rates of change in this section, as well as some behaviors on our graphs of increasing and decreasing. So we are finished with section 1-3. I'll see you again in section 1-4.